Section 2.8 is about absolute value functions and inequalities. What are absolute value functions? So the absolute value of an expression is simply its distance from zero. So what does that mean? Well, think about distance that you would drive. Do you think about driving, let's say, from home to school as positive and school to home as negative? Or do you just simply count the distance and not worry about the sign? Typically, we don't consider this in our everyday lives, but what we're doing is taking the absolute value of our distance, meaning we're not putting it in a system where our distance from home to school and then school back to home is positive in one direction and negative in the other. We leave them as positive in both directions. So, what does that look like mathematically? Well, mathematically, when we say that we have an absolute value function, which is our function here that has the two vertical bars around it, it means that when x is already positive or zero, we simply leave it alone as x. When x is negative, however, we want to turn it positive. And the easiest way to do that is to multiply it by a -1. So essentially what happens is we take any negative value of our x and we flip it over the x-axis and make it positive instead. So we have a positive function on both sides of 0 here. This is our absolute value of x. It's essentially a non-negative function. So non-negative means 0 or positive. So how do we solve these? Well, remember that the absolute value of x is equal to x when x is non-negative, so positive or 0. It's then a -1 times x when x is already negative. So what that means is we have a positive part to every absolute value and we had what was a negative part. So we can find two different solutions to any absolute value equation if we simply look at the positive part of it and the negative part. So if we assume, for example, this one says the absolute value of x minus 5 is 2. So if we simply assume that we have a positive part, let's say it was already positive to begin with. So let's say here's our positive part of our solution. If we assume that x minus 5 was already positive, then we simply leave it alone, set it equal to 2, which means if we add 5 to both sides, we get x equals 7. Well, let's check to make sure that it's true. So remember when we did inequalities, radical equations, we had to check our solutions to make sure they still worked. So in this case, what we're going to be doing is we're going to be checking our solutions to make sure they work, and we're going to find out when we do these with inequalities, sometimes we'll get a solution that would work if this was simply equal to, but when it's an absolute value, it doesn't always work. So let's check it. So for our positive part, we have x equals 7. So let's see, the absolute value of 7 minus 5, does it equal 2? Well, 7 minus 5 is 2. Is the absolute value of 2? 2, and the answer is yes, 2 does equal 2. So x equals 7 is one of our solutions. The other part of our solution is the negative part. And what that means is we take the part of our function that was negative and we make it positive, which means instead of saying that we have x minus 5, well, we replace that with x minus 5 times a negative. So that -1 goes out on the outside, and so we have the negative times the absolute value, which is now just x minus 5, and it equals 2. So if we distribute the negative, we get negative x plus 5 equals 2. Subtract 5 from both sides, we get negative x equals -3, which means x equals 3. And now let's check it and see if this negative solution will work, or the solution to our negative part of our absolute value. So is the absolute value of 3 minus 5 equal to 2? Well, that would be the absolute value of -2. Does it equal 2? The absolute value of -2, remember, we're going to make it positive, so it would be 2. It does equal 2, so we have two solutions. So our two solutions are x equals 3 and x equals 7. Let's try one more. See if you can pause the video here for just a moment and try this one on your own. And then we'll try a couple with fractions together. Hopefully you took a moment to try this on your own. And we're going to look at the positive part first, which means that x plus 3 was already positive. So we just simply set it equal to 7, which means x is 4. And when we check it, is the absolute value of 4 plus 3 equal to 7? Well, that's the absolute value of 7. And does it equal 7? Well, that is 7, so yes. So x equals 4 is a solution. Now let's try the negative part. Let's assume that part of it was already negative, which means we multiply it all by another negative. So a negative times the quantity x plus 3 equals 7. So we end up with negative x minus 3 equals 7. So we add 3 to both sides. Negative x is equal to 10. Divide by the negative 1, so x is negative 10. Well, this is where things can get really interesting because maybe it will work, maybe it won't. Well, let's check and see. Is the absolute value of negative 10 plus 3 equal to 7? Well, that's the absolute value of negative 7. Does it equal 7? It sure does. So we have two solutions to this one as well. Hopefully when you tried it on your own, you got the same answers. If we look at example 3, this example is a little more complicated. So this one, the only reason it's a little more complicated is because it's a fraction. But we're not going to change how we treat this equation. We're still going to look at the positive part and the negative part. So if we assume it started as a positive, then we would have x plus 2 all over 2 is equal to 9. First things first, multiply both sides by 2. Right? Multiply both sides by 2. And we end up with the 2's canceling out, and we end up with x plus 2, and it equals 9 times 2 is 18. So x is equal to 16. And now if we check it, is the absolute value of 16 plus 2 over 2 equal to 9? Well, 16 plus 2 is 18. So is the absolute value of 18 over 2 equal to 9? Well, that's the absolute value of 9. Does it equal 9? And the answer is yes. So x equals 16 is one of our solutions. Now let's do the same thing with our negative part and see if we also get a solution. So for the negative part of our function, we would multiply it by a negative. So negative times x plus 2 all over 2 equals 9. Or we could say that we have a negative times x plus 2 all over 2 equals 9. We can multiply both sides by 2, right, to get rid of, there we go, to get rid of our denominator there. And we have a negative times the quantity x plus 2 is now equal to 18, or negative x minus 2 equals 18. Add 2 to both sides, so negative x is 20, and x is then negative 20. But we need to check and see if it works. Is the absolute value of negative 20 plus 2 all over 2 equal to 9? Well, negative 20 plus 2 is negative 18 over 2. So the absolute value of negative 18 over 2, does it equal 9? Well, that's the absolute value of negative 9. Does it equal 9? Well, that sure is 9, so we would say yes. Our other solution is x equals negative 20. We're going to try one more, and it's also another fraction. So the next one's a little more complicated, but we'll get there in the same way, step by step. So let's try this one. Example 4 says solve the absolute value of 2x plus 3 over 3x minus 4 is equal to 1. So in the same way, we have positive part and we have the negative part. So for the positive part, we're just going to have 2x plus 3 over 3x minus 4 equals 1. And the way we're going to get the 3x minus 4 across is we're just going to multiply both sides by 3x minus 4. So we'll multiply both sides by 3x minus 4 so that we can cancel on the left and move it to the right. The other way you can think of it is cross multiplying, and the 1 is a 1 over 1. So we end up with 2x plus 3 then equals 3x minus 4, because 1 times the quantity 3x minus 4 is still just 3x minus 4. So let's move all the x's to the left. 2x minus 3x is negative x. Move the 3 to the right. Negative 4 minus 3 is negative 7. We end up with x equals 7. So let's check it and see if it works. Now, this is where things can get really complicated if you're not careful, because this means you have to check the original, which means you have to go all the way back to the absolute value of then 2 times 7 plus 3 over 3 times 7 minus 4. Does that absolute value equal 1? Well, this is 17 over 17. Does it absolute value equal 1? It sure does, because it's the absolute value of 1. So yes, it absolutely does equal 1. So x equals 7 is a solution. So let's see what the negative part looks like. And you can imagine this is going to be a little more challenging. So the negative part says multiply by a negative, and then I've got 2x plus 3, and then the 3x minus 4. And we only multiply one part of the fraction by a negative. Because if I multiply the 2x plus 3 by a negative and the 3x minus 4 by a negative, I'd essentially be multiplying by negative 1 over negative 1, which is just 1. And we'd end up right back where we started with the positive part. So make sure when you're solving these, especially when they get a little more complicated and they have fractions, that you don't put the negative in two different places. It only needs to be in one place, either the numerator or the denominator. In this case, I put it in the numerator. And if we multiply both sides by 3x minus 4 again, we get a negative now times 2x plus 3, equaling our 3x minus 4. So negative 2x minus 3 equals 3x minus 4. Subtract over the 3x, I get negative 5x. Add over the 3, and negative 4 plus 3 is a negative 1. So x is negative 1 over negative 5, which is the same as a positive 1 over 5. And you can probably guess that checking this one's going to be a little more challenging than the first one was. So if we check, we're going to have our absolute value, and in the numerator we'll have 2 times our x, which is 1/5, plus 3, and then we're going to divide it by 3 times our x, which is 1/5, minus 4. And does that absolute value equal 1? Well, all we really need to do here is get the same number in the numerator and denominator, even if they have the same sign or not. Because of that absolute value, it'll take care of if one is negative, one is positive. So let's do our fractions. We'd end up with 2/5 plus 3, which is the same as 15/5 in the numerator. The denominator, we're going to have 3/5 minus 4, which is the same as 20 over 5. And does this equal 1? Well, that is 17/5 over a negative 17/5. So does that equal 1? Well, that's the absolute value of negative 1, and it does in fact equal 1. So 1/5 is also a solution. If you don't remember how to do all the fractions with the common denominators, or this was confusing for you on how I checked it, you can also use your calculator. Remember TI 8384. You can use math enter to turn a decimal back into a fraction if it's able to be written as a ratio of two whole numbers. Right. So that's how we manage absolute value equations. And the question then gets really more interesting when we start comparing these over now to absolute value inequalities, which is what we're going to do for the remainder of this section. So if we let x be a variable or an algebraic expression, meaning it could be x plus 5, 2x minus 3, or it could be one of the fractions we just looked at in previous examples, and we let a be any real number such that a is non-negative, meaning it's greater than or equal to 0, so it's positive or 0, then the solutions of the absolute value of x, or our expression being less than or equal to a, are all values of x that lie between negative a and a, meaning The absolute value of x is less than or equal to a if and only if x is between negative a and a. So negative a is less than or equal to x, which is less than or equal to a. The way that we write this in set notation is we say x is in the interval negative a to a. On a number line, what does that look like? It just means on our number line, we have a negative a and a. We are filled in and connected. And now remember, a can be any non-negative number. If we're instead asking where our absolute value is greater than or equal to a, then there are values of x that are less than negative a or greater than positive a, meaning that if the absolute value of x is greater than or equal to a, that is true if and only if x is less than or equal to negative a, or x is greater than or equal to a. And in terms of inequality notation, mixed with a little set notation, we say x is then in the interval negative infinity to negative a with a bracket, so we're including it, union, or in a bracket a to infinity. On a number line, what does this one look like? Well, that means at negative a, I have a closed-in dot going to the left, and at positive a, I have a filled-in dot going to the right. So these are how our absolute value inequalities work. And I will say, oftentimes when we solve the positive and negative part, we realize fairly quickly whether they're going to be in between or they're going to be in opposite directions. So that's the kind of the easier way to remember. Okay, so let's try a couple. So if we determine the intervals on which the absolute value of x minus 5 is less than 2, then really we're not going to start it any differently than we did our equals, right? Our equations. We have a positive part. If we assume that part of this absolute value was already positive, then let's just solve that one first. So in this case, that would be x minus 5 being less than 2, which means x is less than, we'll add 5 to both sides, 7. We're just going to say x has to be less than 7. Okay, that's not too bad. Now let's do the negative part. If we assume we started with a negative part, then we're going to have a negative times our x minus 5, and then that is also less than 2. This is the part that sometimes can be confusing because we don't switch the inequality sign. And the reason being is we're using that definition of absolute value of x, where if x is already non-negative, we leave it alone, but if it is less than 0, so if it's negative, we multiply it by a negative. So this is the definition of absolute value, and we didn't multiply the negative to both sides, just to the absolute value part of it on the left. So that's why we don't have to switch the sign, because we didn't actually multiply it by the entire problem. We are just using the definition here. Okay, so if this is the case, we get negative x plus 5 is now less than 2. And we subtract 5 from both sides. Negative x is less than negative 3. Now when we divide by negative 1, though, something interesting is going to happen because now we have to switch our signs. So when we multiply or divide by negative 1, that means our inequality sign flips. So we now get x is greater than negative 3. Oops, not negative, sorry, positive. X is greater than positive 3. Because a negative divided by a negative is a positive. So if we were to think about this on a number line, right, and these are our x values, and they go from negative infinity to infinity, we have a 3 and we have a 7. The 3 says it has to be greater than that number, so it's going to go this direction. The 7 said it has to be less than that number, so it's going to go this direction. So these two overlap in the middle, which means our true number line then says, okay, I still have 3 and 7, and this is our negative infinity to positive infinity. And what they have in common is that between 3 and 7, they're connected. So our answer would be this number line, or we would say 3 is less than x is less than 7, or we would do parentheses 3 comma 7. Well, what if I change the inequality sign to now be greater than or equal to? How does that change things? Well, let's try it. So we're going to follow the same steps we've done before. So let's see here. So if x plus 3, oops, remember this is our positive part. We have an x plus 3 alone, which would be greater than or equal to 7, which means x is greater than or equal to 4. And if we did the negative part, we would have a negative times the quantity, x plus 3 is now greater than or equal to 7, which means negative x minus 3 is greater than or equal to 7. So negative x is greater than or equal to, add 3 to both sides, 10, which means we're going to have to divide by negative 1 on both sides and switch the sign. X is now less than or equal to negative 10. So this number line looks awfully interesting when you put them together. So here are our x values going from negative infinity to infinity. We have a negative 10 and we have a 4. And at negative 10, it is filled in, but it's going off to the left because it's less than or equal to. And at 4, it's also filled in, but it's going off to the right because it's greater than or equal to. And so in this case, there's no overlap, so we have two distinct pieces. So in this case, our interval would go from negative infinity to negative 10 with a bracket. Then we'd have a union and would start up again at 4 and go on to infinity. So we'd have negative infinity to negative 10 with a bracket, and then a union, and then a bracket, 4 to infinity. And that would change to parentheses if this was just, the original was just greater and not greater than or equal to. It's the equal to that makes things different. If we looked at this from an inequality perspective, that would be x is less than or equal to negative 10, or x is greater than or equal to 4, which is exactly what we found when we did it by hand above. So let's try a couple more and see how it goes. Try this one on your own. Pause and see if you can do this. I'll give you a hint. You have to get the absolute value of x plus 1 alone first, and it's currently multiplied by 5. So consider how you would undo a multiplication and start there. Well, let's see here. Hopefully you tried it and came back. For our positive part, we would have 5 times absolute, or the quantity x plus 1 is less than or equal to 10. If we divide both sides by 5, then we get x plus 1 is less than or equal to 2, so x is less than or equal to 1. Well, that's not too bad. All right, now let's do the negative part. And I'm going to show you that you don't even have to divide out the 5 first. You can do it afterwards. So then we'd have a negative and a 5, and then the x plus 1. And it's now less than or equal to 10. Now we're going to divide both sides by a negative 5, which means we have to switch our sign. So we end up with x plus 1 is now greater than or equal to 5, or 10 divided by negative 5 is negative 2. Subtract 1 more, x is greater than or equal to negative 3. So in this case, if we look at our number line, we have negative 3 and positive 1. Negative 3 is filled in and going to the right. 1 is filled in and going to the left. So this is an overlap situation. So what this tells us is that our number line, in terms of x's, goes from negative infinity to positive infinity. It's going to go from negative 3 to 1, and they're both going to be filled in. Or, forgot the negative down here. Give me a second. There we go. Negative 3 is less than or equal to x, which is less than or equal to 1. Or negative 3 to 1 in brackets. We're going to do one more of these, and then we're going to try a word problem. So one more time, try this one on your own and see how you do. And this time, if you want to, go ahead and divide out the -2 and switch the sign first, and then do the positive and negative parts. You'll find out it would work out the same way as the last one. Or you can leave the -2 there and try it from there. Hopefully you took a moment to try this one on your own, and let's see if we got the same thing. The positive part then would be -2, and then in our parentheses we've got the expression 3x minus 1, and it's less than 10. So if I divide both sides by -2, then I get 3x minus 1, and now remember that means our sign has to switch because of this negative. So now 3x minus 1 is greater than 10 divided by 2. -2 is -5. Add 1 to both sides. 3x is now greater than -4. And x is then greater than -4/3. Which probably feels a little weird because you're used to whole numbers, but that's okay. This is not our first one that's had a fraction. And fractions happen all the time in real life. Let's try the negative part now, which means we had a -2, which makes it a +2. And the 3x minus 1 is less than 10. Now just divide both sides by 2, and we get 3x minus 1 is less than 5. Add 1 to both sides, 3x is less than 6. Divide by 3, x is less than 2. So this one looks like it's going to be another one of those interesting ones that's connected. So let's draw our number line for x, and it goes from -infinity to +infinity. We have a -4/3 on our number line, and we have a 2. So our -4/3 is open and going off to the right because it's greater. Our 2 is open and going to the left because it's less than. So we do definitely have an overlap again. So our number line then is going to look like, if this is x from -infinity to +infinity, here's our -4/3, here's our 2, and we're going to have open circles and connected. And remember, the reason why they're open circles are because we don't have an equals. So if we wrote this one in inequality notation, we would say that -4/3 is less than x, which is less than 2. Or in interval notation, just -4/3 with parentheses because it's not included, to 2, which is also parentheses because it's not included. How does this translate over to these absolute value equations and inequalities to word problems? Well, let's have a peek. Specifications for a rod in an internal combustion engine call for a length of 5.375 inches. Lengths within 0.0025 inches of this length are acceptable. We call this tolerance. So express the tolerance as an inequality involving an absolute value. Use L as the actual rod length. Well, what we know, just based on sort of our intuition or our common sense, would say the rod's allowed to be 5.375 inches, but within 0.0025, meaning it could go from 5.375 minus 0.0025, right? Up to, within, so there's no equal, up to 5.375 plus 0.0025. So if we treated this like a compound inequality like we had before, what that's saying is if I just subtracted off the 5.375, I'd get negative 0.0025, is less than L minus 5.375, which is also less than a positive 0.0025. What this is an inequality. So in the end, what we know is then the absolute value of L minus 5.375. If I want it to be between these two numbers, it needs to be less than 0.0025. And if you didn't want to start from where intuition lands and work backwards, then you can think it through logically. Well, I know that it's okay for it to be 5.375 inches, but it could go up as much as 0.0025 and could be smaller than its given length by 0.0025, which means whatever length I have minus the 5.375 has to be less than the 0.0025, and that's what we're looking at. So the question now is, how do we solve for L in the context of the problem? Well, if we look at our positive side, we know that L minus 5.375 has to be less than 0.0025, or L has to be less than 5.3775. And if we look at the negative, it would be a negative times L minus 5.375 is less than 0.0025, or negative L plus 5.375 is less than 0.0025, or negative L is less than negative 5.3725. If we divide both sides by a negative 1 and switch the sign, we end up with L being greater than a positive 5.3725. So that tells us then that L is less than 5.3775 and greater than 5.3725, which means in the end, L is greater than 5.3725, but it's also less than 5.3775. So those are acceptable rod lengths, and these are in inches. And now that we've gone through absolute value equations and inequalities, you can finish homework 11 on Pearson.